This is lesson 9, and this is a lesson that is going to be entirely lecture, so you won't have an experiment. I do have it written though for you to fill out as you go through and watch the video. The idea is that we're going to look at 3 circuits. We're going to look at a resistor circuit, a capacitor circuit, and an inductor circuit, each of them connected to an alternating voltage source, and we're going to see what effect there is. And then in the next lesson, we're going to put all of that information together in a single circuit, and then you will have an experiment to do with that one. But for this one, we're just going to look at the 3 individuals. So in part 1, we have from lesson 8 the general idea for an alternating voltage source. And when you're writing these things and filling this out, you're going to need to make sure you keep track of the subscripts, because there's a lot of subscripts, and when we put this all together in the next lesson, we are going to have to keep track of the subscripts so we know what all we're talking about. So we're going to start with voltage as a function of time is the maximum voltage. Now this max is always going to be the amplitude of the wave. So if you remember from lesson 8, the amplitude is from the middle to the top peak. It's not all the way from the top peak to the bottom peak. It's actually half of that. So that's the amplitude of our wave, and then times the sine of omega t. So omega t is the part that gives it the variable factor, the oscillating factor. Also remember that omega is 2 pi f, and f is the frequency. So f is frequency in cycles per second. A cycle per second is a hertz, and we talked about that in lesson 8. Omega is sometimes called the angular frequency. So that one will actually be in radians per second. Okay, so if we're talking about a resistor, so I'm just going to put R there. We want to draw a picture. So for our alternating voltage source, we usually just put a circle with a little wavy line to represent a sine wave. We're going to label this as voltage as a function of time, and then over here we're going to draw our resistor that's connected to the alternating voltage source. Okay, in step 2, we want to look at the voltage across the resistor. Well, we're going to start with Ohm's law. We know what that is. It's the sum of the voltage rises and drops around a loop is 0. So at any particular instant, we have the voltage of our source. That's going to be a positive. Even when it's negative, we're going to look at the positive part. So we're going to write it as a positive, and then we have the current. Again, I'm not going to draw the current because the current alternates. So when the voltage is such that this side is positive, the current will come out that direction. It'll go around through the resistor. So then we have minus the voltage across the resistor. Then we're back to where we started, so that sum is 0. Now, we might say, well, the voltage across the resistor is current times resistance, and that's true, and we are going to use that in the next step. But for this one, we want to solve for the voltage across the resistor, because our goal is to write the voltage across the resistor, and then later the voltage across the capacitor, and then the voltage across the inductor in terms of other things. So if we solve this for VR, it's just the voltage as a function of time, but we know from up here that this is V max times sine of omega t. Now, at this point, this is just V max, but since I know where we're headed, I'm also going to put a capital R there. So this is the maximum voltage across the resistor. Now, in step 3, we can use Ohm's law. V is equal to IR. So we can find the resistance, the current, through the resistor as a function of time. So the current is going to be the voltage divided by the resistance. And then this one is actually as a function of time. So this VR of t is our equation here. So we're going to have VR max sine omega t divided by R. Now it tells us in this step that I max is V max over R. So I might put that up here. I'll put so I across through the resistor maximum is going to be voltage across the resistor maximum divided by resistance. So I've just solved this for the current and then written it in terms of the resistor and maximum values. We notice that VR max over R, we have that term here. So this is IR max. So I'm going to put this down here. IR max, that's not what I want. I want IR of t is equal to IR max, which is the voltage over resistance term, times sine of omega t. Okay, so now the important equations, and I might actually put a star by those. When we do lesson 10, we're going to come back and look at various parts, or a few selected parts, of each of these developments. So what we want to keep track of is the voltage over across the resistor as a function of time. So I'm going to put a star here, and then our current as a function of time. So these are important equations, and we'll refer to those in the next lesson. Now we're going to look at graphs. So the first thing we want to do is to draw a voltage graph. It's a sine wave, and we're drawing these qualitatively. Maybe semi-quantitatively. There are certain features that we want exact, but there are certain features that we don't really need to plot a graph up. So what we're going to do is have voltage, and in step 4 you have space side by side. Will we have space? Can we see over here? Okay, I don't need it just yet. We're going to put voltage as a function of time here with the subscript R because it's for the resistor. Now, if we find our voltage equation, it's sine. And sine at t equals 0, sine is 0, so we get the standard sine wave. And I'm going to draw 2 periods. So that's what our voltage looks like. Now, beside that, actually I think I'm going to do it underneath. I'm going to do it underneath on the board, but you will need to draw it to the side on your paper. But I do want to show something here. Okay, so now I'm going to draw my current graph. So this is current through the resistor, and we look at our current equation, and it is also a sine wave, so starting at t equals 0, this is 0, and it will match our voltage equation in form. Now the numbers on the axes would be different, but the form is what will match. So I'm actually going to put a little dotted line here so I can get these, the curves where they're supposed to be. So this will go up, come back down here, it will have a dip here, and a bump there, and a dip there. So this is important to notice that the current graph and the voltage graph look the same. And you might sort of begin to realize or figure out that when we do the capacitor and the inductor, our current equation or our current graph is not going to fall exactly under the voltage graph, but we'll do that when we get there. Okay, then in the box in step 4 it talks about a phasor diagram, and the general idea for a phasor diagram is that it shows current and voltage. It's a vector diagram, and we're only going to show what we have here in this one. The idea is that we will have a phasor diagram for the capacitor and another one for the inductor, and then in the next lesson we'll put all of those together and develop one large kind of an overall phasor diagram. But in order to understand that, we need to do the individuals first. So, the standard rule for a phasor diagram, we have an x and y axis, and then we start with our voltage and current. Since both of these vary together, then we're going to draw our diagram sort of one on top of the other. And for some reason, I decided I would draw a short current vector, and then on top of that, I'm going to draw a longer voltage vector. So this one is I of the resistor as a function of time. Actually, I don't want it as a function of time. I want max. I have to keep track of exactly what I want here. So I'm going to put max, and I'm going to put VR max. Okay? So even though we put it on the same axes, and we know that current and voltage values are different, so we're not exactly plotting these vectors. We are to some extent, but I don't know, this is just the way we do it. So we have current and voltage are along the same direction. I suppose we could have drawn one set of axes with current and another one with voltage, but if you look this up in the textbooks, you will always find all of these things on the same phasor diagram. Now, the other thing that it says in the box is that this diagram rotates in time. So it rotates counterclockwise in time, and at any particular instant, the projection of these vectors onto the y-axis is the actual value that you would measure in the circuit. Now, there's a problem because you aren't going to be able to measure current or voltage at a particular instant, because if we have 60 cycle voltage, it's making 60 circles in a second, and so your meter or you are not going to be able to physically measure anything at a particular instant. Now, most of the time in textbooks, you usually don't actually do a projection and calculate the voltage or current at a particular instant. You could, but there's usually no point in doing that because you aren't going to be able to measure that. So there are other reasons why we have these phasor diagrams, and by the time we get about midway through the next lesson, you'll kind of understand the purpose of them. So the purpose is usually not to ever determine the current or voltage at a particular instant. And I have not made up any problems or assigned, or you aren't going to have any homework where you would actually have to do that, because there's really not much point in doing that. Okay, so for our resistor circuit, we have the circuit, a resistor in series with an alternating voltage source. We have sort of derived an equation for the voltage as a function of time and an equation for the current as a function of time. We have drawn graphs, one for voltage, one for current, and we have put these two together in a vector form in a phasor diagram. So this is basically what we're going to do, or something similar, for the capacitor and then for the inductor. So I need to erase some of this. Okay, I'm going to erase. And I'll erase the current one, and I will erase that. Okay. So now, you as the student, you'll have to actually write some of these things. It used to annoy me when a teacher would go through on stuff that was on the board and just change one little thing, that I had to write everything. But now that I'm a teacher, I can do that. So, we're going to start with a capacitor. Oh, I need to change this. So we're going to start with a capacitor. We're going to draw the symbol for a capacitor. It's two parallel lines, the same length. This is the capacitor. Our alternating voltage source is still the same. It has the same format. We still have Kirchhoff's rule. The sum of the voltage rises and drops around a loop is 0. So the voltage from our source we have as V of t, and the voltage across the capacitor is V of t, but with the subscript c. So now then, again, we want the voltage across the capacitor. So we have a C there. Oh, have another C over here. Okay. So the voltage across the capacitor oscillates like the voltage of the source. Now, we need, let's see, okay, that looks right. Now we need to do something with current. And actually what I'm going to do, if you've been writing things, you'll have everything right. I'm going to write this a little bit smaller, so then I have some more room. V of t minus V C of t equals 0. And then this is going to be VC of t is equal to VC, actually, let's do this. Of t equals VC max sine omega t. Okay, that should be what I had down here, except it's moved up a little bit. Okay, so in our phasor diagram over here, we had voltage and we had current. Now, what do we know about a capacitor? We normally don't have an equation for current, except I think I did at the end of lesson 7 in unit 1. I talked about current and had some equations and graphs there. But the important thing is we want the current. Now, something else you have to think about is, for a capacitor, this is an open space or an insulator. There is not going to be any current actually going through, totally through the capacitor. What we're looking at is current in the wire. So when the current gets here, the actual charges are going to go onto the plate, and there will be a charge on the plate. And this is what you did in lesson 7 at the end of the other unit. But we still call it looking for current. Now, we know in general, back from one of the other previous lessons, that the current, it's the rate of flow of charge. So, it is delta Q over delta T. But we can't really do anything with that with any of our equations. What we need to do is write this in terms of calculus. We need to write the time derivative of the charge. So dq over dt. And if you haven't had calculus, I think most of you have, or if you don't remember it, that's okay. Just write down what I tell you here, and then it'll make sense in a little bit. Okay, so now we need to look at an equation for charge on a capacitor. So I'm going to put that over here. The charge is the capacitance times the voltage. So what we want to do here is the derivative of the quantity C times V. Now, you should recognize C is the capacitance of the capacitor. That's a constant. So if you're taking the derivative, you can bring the constant outside, and then you have C times dV dt. So that's what we're actually going to do. And our voltage is the voltage, the time-dependent voltage across the capacitor. So I'm going to go ahead and put a subscript C there and put that as a function of time. Okay, so now we're just about ready to do this. So we start with our C. Now, the derivative of the voltage. So we look at this expression here, the Vmax times sine of omega t. Well, the Vmax is also a constant, so we're going to write that, Vc max. Now we need the derivative of sine. So if you go back to your calculus, the derivative of sine theta is cosine theta times the derivative of the theta, or the argument. So we write the derivative of sine is cosine, so we put cosine of omega t. And actually I'm going to move that over just a little bit. That doesn't erase very well. I'm going to put it over here, cosine omega t. Then we need to take the derivative of the argument of the cosine. And this is what they in calculus usually call the chain rule. So derivative of sine is cosine of whatever, and then the derivative of the argument with respect to time is just the omega. So that's like saying the derivative of 3x is 3. So the derivative of omega t is omega, and we're going to put the omega right there. So now we have an expression for current, and I need to make that as a function of t. So our current, and it's across the capacitor, so we'll get all the subscripts in there. Okay, so what we want to do with that, a couple of different things. We could leave this as cosine, but since we know where we're headed, or at least I do, or whoever's writing the textbook, we're going to make some adjustments so that things are a little nicer to deal with later. Okay, I don't really want to leave this as cosine. I really want it in terms of sine. So we can't just change cosine to sine because they're not the same. But we know that cosine is related to sine. And I think I will put that up here in red, maybe right along in here. It's in the write-up as well. But cosine of theta is sine of theta plus pi over 2. Now when we're writing these, I normally write pi over 2. If you're doing anything with it, you remember that pi over 2 is 90 degrees. So this just tells you that sine and cosine have the same shape, except that they differ by 90 degrees. And we'll see how that affects when we're drawing our current graph there. Okay, so I want to change this. I'm going to put C VC max times omega. Now cosine, and up here we normally just write the identities with theta, but theta is our omega t. So we're going to change our cosine to sine, and then we'll have omega t, and then we'll have plus pi over 2. Okay? So that's our equation for current. And at this point we could actually plot the current, except before we do that, I want to introduce another quantity and sort of adjust how we write the current. Well, if you look back to the resistor problem, what we had in front of the sign was VR max divided by the resistance. So it would be nice to do something similar to that here. Well, what we're going to do is, if we're going to look at C times omega, actually I'm going to call it omega C. So we're going to do a little bit of math. So omega C is 1 over omega C. So if you divide and then divide again, then you end up with the same thing. Okay? So what we would like is something in the denominator here that is in the same position as the resistance was in the resistor problem. So we have our 1 in the numerator, and then we have 1 over omega C in the denominator. So we're going to define this quantity as capital X, and it's going to be called reactance. It's not a resistance in the same sense that you have resistance of a resistor, but it behaves similar to that, or it's analogous to that when you have an alternating voltage and current. So it's not called resistance, it's called reactance, and it is labeled as capital X with the subscript C. Note that it's just this 1 over omega C. So what we can do next here is C times omega is 1 over the reactance. So we're going to leave our voltage max in the numerator. We're going to put our X in the denominator. And then we still have our sine of omega t plus pi over 2. Okay? So we have one more step to get it to be in the format that we would like. And in step number 6, we want to write the current. And it tells us that VC max divided by the reactance is the current max for the capacitor problem. So we're going to write this, okay, over here we're going to have the current for the capacitor as a function of time, and then this part right here is going to be I C max, and then we have times sine of omega t plus pi over 2. So this equation looks like our equation for current, except instead of a current, maximum current for a resistor, we have maximum current for a capacitor. And probably the easiest thing to think about, since you know that the current's not really going through the capacitor, is to think of this current as in the wire just before it gets to the capacitor, or they're very close to it. Now, it's actually the same all the way around because we know that current in series isn't the same at all points. But since we have a subscript C, that sort of draws our attention to the capacitor, so we can just look at the wire very close to the capacitor. Okay, so let's put our stars by the two important equations. We have our voltage here across the capacitor, and it's in terms of maximum voltage and sine of omega t. Down here we have current for the capacitor. It's in terms of current maximum and sine of omega t, but we still have this other little term out here. So we have our two relevant equations. Then we want to draw our voltage and current diagram or graphs, and then the phasor diagram. So we're going to do exactly the same thing for this that we did for the resistor. Well, I didn't change the graph or equation for the current for the capacitor, so we still have the same graph. Here it's a sine wave at t equals 0. This is 0, so it starts here, and I have the two periods. So that's what will go in step 7. And again, I'm going to draw the current underneath, although you on your paper will have to draw it beside, unless you drew it kind of small, and that would be fine. So I have my y-axis and x-axis. This is going to be current at the capacitor. Maybe that's what I will call it, is current at the capacitor, because it's not across the capacitor and it's not through the capacitor. So if we just say at the capacitor, that should be sufficient. So we'll make that a C. Now, we need to look at our equation here. This is our amplitude, but if we look at the sine term, it's omega t plus pi over 2. And if you remember from trig, they were always talking about if you add a phase here or subtract something, that could tell you which way the wave was shifted. And I always had a hard time remembering whether you add and subtract and which way you shifted. So the easiest thing to do, to make sure you get it right, at t equals 0, this is 0, but you still have pi over 2. Pi over 2 is 90, so sine of 90 degrees is 1. Okay, so at t equals 0, this is going to start up here at its maximum value. Now, we know it's a sine wave, so all we really need to do is think of the sine wave here, and we're shifting it to the left pi over 2 so that this tip, this point up here, is on the axis. And actually, I think that sounds right, because if you add here, then you move the wave to the left, which always seemed like backwards to me. But if you just remember that that's what you do. Whatever you have here, then you move your graph the opposite direction. So if I'm adding 90 degrees, I move my wave 90 degrees to the left. So I'm going to go ahead and draw these dotted lines down here. Now, I have to make sure that I have my wave shifted. So this peak is over here on the axis, which means that where this crosses the axis, this point is going to be over to the left by 90 degrees. So under here, this is going to go across the axis here instead of over here. Okay, so what I can do then is go through and at the middle of these regions put my points, and then this is going to be a dip that's going to come back up and go through here. It'll come up and go across here, even with that. It will go down through the axis there, go down, come back up through the axis there, and then up to a point like that. So if you can draw these very nicely, you could actually draw one of these, I don't know, on really thin paper and then put it underneath or put it on top, or have the thin paper on top and then move it over and then actually trace it. But the important thing is that this current is shifted 90 degrees to the left of the voltage. So when we draw our phasor diagram, and I think for right now I'm going to erase this so I can use this space here. For our phasor diagram, we have to get that information in our picture. So what textbooks normally do is we have our voltage equation in terms of sine. So previously for the resistor, we drew our voltage vector up here. So VC max. So we're going to again draw our voltage vector in quadrant 1. Now we have to get our current vector oriented properly relative to the voltage vector. So to do that, it's 90 degrees counterclockwise from the voltage. And I don't know, you might think about it for a little bit, but that's what it is. So the current comes up here, and the actual length that you make the vector doesn't really matter. But on the resistor one, I had the current about here and I had the voltage about here, so I'm going to sort of keep that. So this is I at the capacitor max. And then note, and you might want to actually draw this, these are perpendicular, so I'll put the little square there to show that the current is perpendicular to the voltage. They're different by 90 degrees. 90 degrees is perpendicular, so the 90 degrees is the pi over 2. Okay? So now we've done the same thing for the capacitor that we did for the resistor. We start out with our diagram. We apply Kirchhoff's rule. We have our voltage is oscillating, has an amplitude of V max, oscillating with sine omega t. And then we want current. We have to figure out how current is related to a capacitor. We know the definition of current is the time derivative of charge. Charge is C times V for a capacitor. So we put all of this information in, take the derivative, get it in terms of cosine, use an identity to get it back to in terms of sine, and then we define a new quantity called the reactance in terms of omega and C, and then we have voltage over reactance, and we have that as our current. So this matches nicely, or is analogous to what we did with the capacitor. Now, just as a side comment, because this lesson is mostly from the math point of view, but just to sort of point out something that you should have figured out kind of in the middle of lesson 7, which was on the capacitor. You remember that when you had the circuit set up, when you closed the switch, the light was bright immediately and then it dimmed out. So it was bright because the charges could flow easily, so you had a large current, but there was no charge on the capacitor. After the capacitor got charged, then there were no more charges flowing, so the current was 0. So that's what you can look at here. You could think of this as closing the switch. The voltage across the capacitor is 0, but the current is a maximum. And then after the capacitor gets charged, then there's no more current because the charges are not moving. Now, in lesson 7, you just did that, and that one thing happened, and then that was the end of it. But here, since the voltage is oscillating, the capacitor charges one way and then discharges and charges the other way and oscillates back and forth. And so, if you look at our definition of reactance, which I just erased, but I'm going to put it back up here. Our reactance was 1 over omega C. And reactance has to do with the effect that the capacitor has in the circuit. So you could see that if the frequency is low frequency, that means the current is going one way for quite a while and then the other way for quite a while. So if it's going one way for a while, the capacitor has a chance to actually become charged. Now, if it's high frequency, the frequency or the voltage is oscillating back and forth so much and so fast that the capacitor really doesn't have much of a chance to get charged. So, at high frequency, we have a number in the denominator. If you have a large number in the denominator, the overall effect is a small number. So, this reactance for the capacitor at high frequency in the denominator, you get a small number here. It really doesn't have much effect. If it's a low frequency, then you have a small number in the denominator, so that makes the overall fraction larger. So it does have more of an effect if the voltage is oscillating at low frequencies. Now, we haven't talked about what low frequency is and high frequency, but we'll do that in the next lesson. Okay, so we've gone through and we have derived our equations for voltage and current. We have our graphs for voltage and current, and we have our phasor diagram for voltage and current for the capacitor. So now we need to do the same thing except for the inductor. So I'm going to erase certain parts just like I did before. I'm going to erase that and that. We don't need that equation. We're going to put an inductor there and there. Our current is going to be completely different, so we're going to erase all of that and that. And then our equation here is going to be in terms of an inductor. Okay, I don't really like this V. It looks like something else. More like a V. Okay, an inductor is a coil. So to draw a coil, we usually just do a little thing like that. And the inductance is called capital L. Why it's capital L, I don't know, but it is. So we're going to be talking about an inductor. We have an inductor in our picture. We have an alternating voltage source, the same thing that we had. So for Kirchhoff's law, we have the voltage of the source, and then here is the voltage of the inductor. So for the inductor, we solve this, and then we have V max for the inductor times sine of omega t. And so that all pretty much stays the same as what it did before. Now we have to figure out what do we do with current. And current in an inductor, and basically inductors are a little more complicated to deal with than capacitors. But I'm just going to do it and see the end result in just a minute. Well, a coil, and I think I described this a little bit at the end of lesson 7. A coil, of course, has a coil, and when you have current going in a circle, it produces a magnetic field through the center of the circle, and then there is a voltage as a result of that. And the idea is that the coil tries to keep the current from building from 0 up to some value. And that is related to Lenz's law. So at this point, we really don't need to go into those details, but that's kind of what's happening. Okay, so the equation that we're going to look at to help us figure out current is that voltage across an inductor is equal to L, the inductance, times di dt. So the voltage does depend on the inductance of the inductor, but it depends on the rate at which the current is changing. It's not the current, but it's how fast the current is changing. So from this, we need to figure out what to do. Well, again, we have to do a little bit of calculus, and we're going to integrate this time. With a capacitor, we'd had to take a derivative. Now we have to integrate. So I'm going to move the dt over to one side, leave the L over here with the di. So I'm going to have V sub L dt, is equal to L times di. Now the symbol for integral is this long thing like that. It's sort of supposed to be an elongated S for summation. Now on the right hand side, the inductance of the inductor is a constant, so we don't need to put it inside the integral. We will just leave the di inside the integral. Now on the left, our voltage across the inductor, if we go up here, this is the thing that is a function of time. So we need to put our integral sign outside so that we can actually integrate our voltage equation or term. So we're going to put this VL max sine omega t dt is equal to L integral di. Now, since VL max is a constant, it can be outside the integral, so I'm going to actually put my integral sign right there. Okay, we'll do the right side first because it's easy. So L and the integral of di is just I. Okay, now on this left side, the integral of sine of omega t. So if you go back to calculus, the integral of sine is minus cosine. So we'll start with our VL max, our constant. The integral of sine is minus cosine. And then instead of multiplying by the derivative of this, we have to divide. And if you don't remember doing that, that's okay. when we get to our equation down here, that's what's important. But I wanted to show you where these equations come from instead of just coming out of thin air, I guess. Okay, so now I want to solve for this I. So I'm going to have I for the inductor as a function of time is equal to, and actually I'm going to do a couple of things since I'm kind of running out of space. Remember we had an identity for cosine, so oh, yes, that was cosine. This is not cosine, this is minus cosine. So we have minus cosine of theta is equal to sine of theta minus pi over 2. So minus 90 degrees. Okay. So that's why I left the minus sign here with the cosine. Okay. So now then, we're going to have VL max, and then for minus cosine of omega t, we're going to put sine of omega t minus pi over 2. Now we're still not quite done because we have this omega here and then we want to divide by this L. So I'm going to put divided by omega times L. Now, that looks very similar to what we had for the capacitor, except the capacitor had omega C in the numerator. We have omega L in the denominator. And to make this look like the equation with the resistor, we had resistance in the denominator. And for the capacitor, we did omega C equals 1 over 1 over. So what we need now is to define a reactance for the inductor. So I've got a lot more space here than I had before. So the reactance for the inductor is omega L. And by doing that, then we can have the current through the inductor as a function of time is I inductor max times sine of omega t minus pi over 2. And then it tells you in here that IL max is VL max over XL. Okay. Now, let's look at this in terms of high frequency and low frequency. So the idea here was that the inductor behaves or has an effect when the current is changing. So if the current is changing rapidly back and forth, which would be for high frequencies, then this is in the numerator, so the reactance is going to be significant when the frequency is a high frequency. If you have a low frequency, then it's going one way and then going the other way, so it's not changing very fast. So the reactance would be small because this di dt here would be small. So for small or low frequencies, you get a small inductance or a small reactance. Okay, so we're going to mark our appropriate equations. Our voltage equation is the same sort that we had before. Now we have a current equation down here that looks a lot like our capacitor equation, except this is minus pi over 2 instead of plus pi over 2. So we have our voltage graph for the inductor. So we have this. And remember that that has stayed the same. Now we're going to draw our current graph underneath that. So we have I of the inductor as a function of time. We're going to draw or extend these dotted lines down here so we can line things up. Now, let's look at this. What happens to the current at t equals 0? Well, we have sine of minus pi over 2, which is sine of minus 90 degrees. And sine of plus 90 degrees is a plus 1. Sine of minus 90 degrees is a minus 1. So this starts down here. Okay? Now, the way to think about this, you might say, well, how am I going to get anything out of this to be down here? So I'd have to move this way over to the left. Well, we don't do that. What we do is we go back up to our voltage graph and we draw the preceding bump or dip in this case. So this will be like this. So the easy thing to do now is shift our voltage graph 90 degrees to the right. And that matches our rule before that seemed to always be backwards to me. When in the capacitor, when we had a plus pi over 2, we moved the graph to the left. Now that we have a minus pi over 2, we move the graph to the right. So if we shift this to the right, then this becomes here. It crosses the axis here, and here, and here, and here. So it goes over and up, and then we have a peak, and then back down through the axis, down, up, down, and over to there. So our current graph looks like this. Now, our phasor diagram, we're going again to put the voltage in the same position, the first quadrant, and I'm just picking a sort of an arbitrary position here, just up a little bit, I guess. So this is voltage across the inductor, max. Oh yeah, just max. Now, what about our current graph? Where does our current vector go relative to our voltage vector? So, our voltage vector is going to go down. Have to make certain. Yes. Actually, I'm not sure what I just said. The current vector. At t equals 0, this is minus 90 degrees. Minus 90 degrees is down this way. So I'm going to draw my current vector here. Current inductor max. And this is 90 degrees. It doesn't look quite like it's 90 degrees on the board, but it's supposed to be. So now we have our voltage vector up here. We have our current vector here. So again, summarizing, we have our equation with the alternating voltage source. We have an inductor. We start with Ohm's law. Not Ohm's law, Kirchhoff's law. We find the voltage across the, across the inductor. We start with our definition that relates voltage and the rate of change of current. We go through the calculus part to integrate. We introduce a new term for reactance for the inductor, which is omega L. And we have that in here to get us with the maximum current for the inductor. And then after we did our integration and got back to a sine term, we ended up with sine of omega t minus pi over 2. And that means that we needed to shift our voltage graph 90 degrees to the right, so we end up with this. And then we draw our phasor diagram, so we have voltage in the first quadrant as we have had before, and then we have the current vector 90 degrees from it in the proper direction, so it's down here. So what we're going to do now, this is all we're going to do in this lesson. There are some questions and a couple of places for you to calculate reactance for an inductor and a capacitor. But the next lesson, we're going to sort of have a very quick review of this, and then we're going to put all of that together and see what we end up with in a particular circuit.